Hello, I'm Abdurrashid from Khalifa University, Abu Dhabi in the UAE. I'm going to briefly present the contribution of a paper I co-authored with Dr. Bashar Al-Hussauna that discusses a large-scale suction-based climbing robot we developed at the university for a building maintenance application, namely wall painting. Making a robot climbing is challenging as it should move against gravity. In an unmanned ground vehicle or an unmanned water surface vehicle, the gravity is naturally countered by the ground and the water respectively. However, in a climbing robot, particularly the one climbing a vertical or overhead surface, typically there's not any structure that directly resists the weight of the robot. Hence, we need to find a way to prevent the robot from falling down while it moves. The challenge in making a robot climbing also depends on the type of the climbing surface. To make a robot climb a steel or ferrous surface, we can simply use magnetic adhesion. To make a robot climb a slender structure, we can use mechanical adhesion, such as using grippers, claws, or a set of wheels that altogether hold the slender structure. To make a robot climb a non-ferrous surface, we can use negative pressure adhesion, such as a vortex chamber or some suction cups. We could also use some sticky pads or fibrillae, like in some animals, but this technique seems not scalable. Labonte et al. Concluded in their paper that a Spider-Man cannot exist, and the reason is because geckos are the size limit for sticking to walls using sticky pads. They observed that around 4% of a gecko's body should be covered by sticky pads to make the gecko stick to the wall. And a human would need to cover 40% of his or her body with sticky pads to be able to stick to the wall. This is definitely not practical. Hence, making large robot that climbs a non-ferrous flat surface is very challenging. It's like expecting a crocodile, an elephant, or even a human to climb on a non-ferrous flat surface. Our contribution is developing a large climbing robot that using suction cups to climb a non-ferrous surface. This climbing robot is an improved version of our earlier robot. From the data in this table, we can see that both our predecessor and current robots have much larger mass-to-volume ratio compared to crocodile, elephant, and human. As we can see in the table, crocodile, elephant, and human have only a ratio from 400 to 1,000. Our predecessor robot has a ratio of more than 4,000. Compared to the predecessor robot, our current climbing robot has larger size with less mass-to-volume ratio, that is slightly more than 2,000, thanks to the optimization of the structural design and material selection. Maybe you would ask, why a large climbing robot? Well, some applications require a capability to handle large payload. Also, we developed a large climbing robot to assess the scalability of a robot climbing on a flat non-ferrous surface. Regarding the parallel kinematics used in the climbing robot we developed, it has some advantages, including high rigidity to mass ratio that leads to a capability to handle large load manipulation. It also requires only 3 actuators for both locomotion and manipulation besides the suction cup. Its parallel kinematic design also makes the robot's center of gravity close to the climbing structure. This increases the robot's stability and reduces its locomotion effort. Here we can see the robot is climbing up and down. The climbing motion is achieved by synchronizing the parallel mechanism motion and the suction control. In particular, there should be an attachment overlap between 2 consecutive steps to ensure the safety of the robot operation. We also optimize the trajectory of the parallel mechanisms and effector to increase the attachment success rate. This is achieved by approaching the climbing surface and departing from it in a perpendicular direction. Finally, here we can see an application of the robot, namely wall painting. To perform a painting task, the climbing robot stops at a certain position and sprays the paint to the wall. We can see here how the developed climbing robot is equipped with a modular painting extension to perform a wall painting task. Two types of painting extensions were developed and tested. One is a 1 degree of freedom painting extension that moves in X direction back and forth. The other one is a 2 degree of freedom painting extension that moves in X and Y directions such that it can paint a larger area within a single position of the climbing robot. To sum up, we demonstrated that the proposed climbing robot built at a large scale can successfully climb on a vertical non-ferrous surface. We also demonstrated that the robot design conveniently allows an application for building maintenance, namely painting. Future work would include static and dynamic theoretical analysis, experiments to obtain more quantitative results, testing horizontal motion of the robot, adding a rotational degree of freedom to allow the robot to rotate when climbing, adding vacuum sensors to indicate a successful attachment and eventually increase the climbing reliability, and using the robot for other high rigidity applications such as cleaning and drilling or coring of vertical non-ferrous surface. Thank you.